I always wanted to be a plant biologist because I've always believed that plants have the ability to save the Earth on their own. The problem of global warming is one we can't turn our backs on. We have to use every means at our disposal to stop it. In fact, stopping it isn't enough. We need to roll it back to where we were 30 to 40 years ago. That's the objective of this project, Cool Earth, returning the Earth's climate to its condition 30 to 40 years ago. I believe the key to this task is plant biotechnology. Gene optimization, distant hybrids, and optimization of microbial symbiosis are all different technologies operating on different principles. Rather than focus on a single point, this project adopts a number of approaches simultaneously, but with a single goal. By integrating different technologies operating on different principles, we aim to achieve double or even triple the effects of more conventional research. Let's start with gene optimization. Gene optimization is the idea that genes inherent in plants can be optimized using gene manipulation, genome editing, and so on. The key here is that we're talking about tiny changes to the genes of individual plant species, leveraging the strengths in plants to maximize advantage. We're mainly looking at master genes that produce lignocellulose in plants. If we can improve the genes that produce lignocellulose, we can increase biomass. Species we're focusing on include larch, poplar, and eucalyptus. Increasing lignocellulose increases biomass, which in turn increases CO2 fixing capability. At the same time, denser trees are stronger trees, whose durable wood becomes more useful for construction. Next, distant hybrids. These are plants that are hybrids of species that cannot form naturally because they are too far apart genetically. We bring the species together using technologies such as in vitro fertilization and cell fusion, creating new plant species. For example, Japanese pampas grass is resistant to cold, but it's small, whereas the Poaceae rice family plants of the tropics are large. Can pampas grass and tropical rice family plants be combined to create a large grass that is resistant to cold, thereby fixing plenty of CO2? We're pursuing this line of distant hybrid research in a scheme to reduce petroleum consumption by generating electricity from this hybrid biomass. Finally, in optimization of microbial symbiosis, we search for microorganisms in nature that promote the growth of plants. Results have emerged that show a 20 to 30% increase in plant biomass from the exposure to these microorganisms. Increasing biomass is no simple matter. It is known, for example, that increasing the lignin content of a plant makes it grow slower. So, our task is to find a judicious trade-off that boosts biomass productivity. It would be amazing if we could do it, but the challenges are formidable. I want to be a part of creating a society in which people and all kinds of living things can live happily and in comfort. Imagine how beautiful Tokyo would be if its skyline were filled with high-rise buildings made of wood. It would be a city like a forest, an eco-city. Of course, this project won't accomplish that on its own. But if we can bring the business and political worlds on board, they may plunge ahead and make the dream come true. Our research and development project applies 3 distinct technologies aiming to dramatically increase the CO2 uptake in plants and create stronger trees.
NEDO